thanks for coming, and I hope that this presentation is interesting and valuable to the audience. I have to admit, I had a million ideas for this presentation, pages of notes, so much I wanted to talk about. And I think that there's so much nuance and depth in this subject that I found it very difficult to be happy with my results. So please ask questions, please comment. I would say throw things, but it's not going to work very well. And I hope everyone finds something to take away from this, because it is something I am strangely or oddly passionate about, despite its rather mundane title, right? So, hi again, I'm Ethan Stern. I'm a CLA, an embedded developer, and I think still a CPI, though it's been a little while since I taught a LabVIEW course. I'm a managing partner at Composed Systems. Composed Systems is 5 full-time CLAs, 4 in the US, 1 in Canada. We do for hire software development. We work with startups and biotech and manufacturing, and we do team development most of the time using Scrum. There's a lot of interaction between team members, a lot of code reviews, and another way that we collaborate beyond project work is by contributing open source code to the broader LabVIEW community. We eat our own cooking. We use our open source on our customer jobs all over the place. Our framework gets used everywhere. Our test executive gets used many places, and we have a lot of big open source. We have a lot of little open source. We've learned a lot by building that tool chain and by maintaining it, and teaching other people how to use it. And recently, we achieved NI's Center of Excellence certification as a development team. So today we're going to talk about functional programming, all this stuff. We're also going to talk about all this stuff. You can tell from all the information that you're absorbing that I'm really into Nassim Taleb and philosophy and Buddhist philosophy and all kinds of interesting things. Right? But really one of the central ideas, I think, that comes up for me when I'm talking about errors and error handling is this idea of having empathy for yourself. This isn't having empathy for information itself, but having empathy means, to me, thinking about your customer who's going to see the error code flash up on the screen. Think about your teammate on your development team who's going to see the errors that are coming out of your API. Think of yourself 6 months from now when you're consuming the driver code that you wrote, and you would very much rather forget about the 300 pages of Oriental motor, motor drive documentation that you had to read in order to get it working. So think about that person. We have all of these programming style guides and rules in place right there, and these are not controversial rules. It's like, a VI should fit on one screen, right? Of course, there's always a guy in the room who scoffs at that rule, but these rules exist to make our code easy to reason about. And I think that error codes should also be easy to reason about. They should be curated, maintained, and returned as values in a way to make our lives easy and to make us look good. And I think probably everyone is struggling nowadays with information overload. I have dozens of emails from God knows where, but also my kids' teachers about things that are going on in their classrooms, and it's like I can't even process that information. There's too much information. So, we help ourselves out when we think ahead and think downstream. Joking agenda aside, what we're actually going to talk about in this presentation are some grounding concepts about Labview, about why I feel this way about errors, why I think that these opinions and comments I'm about to make are justified. We're going to talk about something that I discovered in the past few months, which was really groundbreaking for me, which is the concept of exception, or in the case of Labview, error types. It turns out some people have done some good work, especially this guy named Eric Lippert, who I will introduce you to. We're going to talk about how context matters. A strategy for anything might be appropriate at a particular level or in a particular place, but that does not mean that it's appropriate for every place. And then, because I am just generally obsessed with the solid software design principles, I'm going to show you that they actually just tell us what to do when it comes to error handling. So what is functional? I mentioned functional programming in at least one of my agendas. I argued this at the last CLA summit, and a lot of people agreed with me. Labview is inherently a functional language. A functional programming language is built for robustness. It's built for to be easy to reason about. Functional programming uses functions and immutable data to do work. Data goes into a function, it gets operated on in some specific way, and then it comes out again. For a long time, I struggled understanding what this meant, this very simple concept, until I did some, really not much, but just found the right thing to read. And that sort of opened the door to thinking about Labview as a functional language for me. And nowadays, when I'm thinking deep thoughts about Labview, it's usually something having to do with functional programming. Immutable data doesn't mean that the data can't be mutated ever. It means it can't be mutated within the scope of that function by something else. So when it's being operated on by that function, right? We're looking at a VI. It takes in an object data cluster. It takes in an error. The values I get out are not going to have any race conditions with values that could have been manipulated elsewhere in the program. This is functional. All right, mutate, we're not talking about the ooze, we're talking about changing values. All right, so we have conventions in Labview, right? We generally acknowledge that data flow is better than local and global variables. We might use functional globals when they serve a specific purpose, right? They kind of give us a singleton pattern and other advantages that I'm guessing most everyone here knows about. But is branching data good or bad? I mean, it's appropriate in different situations. We just want to gain access to some data on a wire, right? We don't mutate that value. That's why the read self or read call or uncure method in the actor framework doesn't give you back an actor data cluster. It's obviously not mutating the value on the wire. It's just accessing data on the wire. So it gives us the value of the thing that it picked off. However, you might have a function elsewhere that operates on that wire, and that function might mutate the data on the wire, and therefore it's going to take it in and give it back to you. I believe I was first introduced to this concept in Labview by Darren Nattinger's Brainless Labview programming presentation that he gave probably 3 years ago at the CLA Summit, I think. A lot of assumptions there, I don't actually remember, but it was a great presentation, and he showed the classic Labview railroad tracks, right? And he said, please don't do this. And at the time, a lot of my programming looked like that because I was starting to get into object-oriented programming. If you have a function that does not mutate, alter the value on the wire, then don't wire in and out. Wire in and have parallelism in the execution of your code, because you can branch a wire and send it somewhere else, because you know that in this case, this fill function doesn't need to finish before you can use the value on that wire somewhere else. In this case, I am telling you that it does need to finish because I'm giving you a modified value at the output terminal. Right, so we're going to jump right into the error stuff now. Eric Lippert's 4 exception types. This guy is from what I can tell, a rather well-known and respected developer. His post I first discovered on MSDN, and then I found it on his personal blog. So if these slides end up getting shared, I have a link to the blog post from which the following few quotations have been clipped. So we have 4 exception types: fatal, boneheaded, vexing, and exogenous. Right? And just like in anything, when we have something as flexible as an exception or an error cluster in LabVIEW, being able to categorize these things really gives us some signposts about how they should be handled, where they should be sent, and how much they should be tolerated or expected. And again, if I use the language of exceptions, we don't have exceptions, we don't have error or exception classes in LabVIEW, right? We just have this value cluster that gets passed around. But when you consider how functional LabVIEW is as a language, I think that we can do a lot of powerful things with that value of that cluster. All right. So fatal exceptions are not your fault. There's nothing you can do about them. There's nothing you can do to save it. Ship's going down. When the ship's going down, you're right, the last thing I'm worried about is closing references. I mean, the application might be crashing. It's basically this. I don't need to do anything about Sub-Zero's disembodied heart. It's game over. What kind of stuff in LabVIEW can generate that? This is the example I came up with. Right, I have properly wired that obtain queue function with all of the inputs it needs. If I can't obtain that queue, there's something seriously wrong going on. So fatal error, what can I do to recover from this? I mean, at this point, if I get an error out of that output, I think my application is doomed and it's crashing. Right? So I'm not going to waste any time thinking about that error. I might want to wire that to something, but I'm not going to write error handling code. Right? There are only 4 or 5 error codes I can get out of that function. But with the way it's wired, none of those make sense other than possibly error 2, which is that the application's out of memory, which means, you know, the ship's going down anyway. Which brings us to our next type of error, boneheaded errors or exceptions. Your own fault, you could have prevented them. Another word for this is a bug, right? So what do we do with these? I've seen a lot of code over the years where people handle errors in one particular place. They might have a loop in you know, the pre-actor framework days, or a consumer that was called an error handler. And they would just throw all of the garbage at it. I think that is a terrible design pattern. There are certain places we're going to have default error handling behaviors. I think that what you can do when you get a boneheaded error in your application, right? If you knew it was going to happen, you wouldn't have programmed it in the first place. You have 2 reasonable options, in my opinion. You can log it, clear it, and try to keep going, or you can log it and shut down. And in my code, I don't think there's much else I try to do. You know, the cool thing is, if you're using logging, which I hope you are, every boneheaded error is an opportunity to make your code better. Right? I hope you trap it in the event log You can go back and figure out what went wrong, what was the first error that occurred, maybe even figure out where it occurred, and fix your code. All right, so there's nothing we can do to stop this. We can just use the tools of our trade to try and catch them and try and do a reasonable thing. I guess the only thing I'd like to add is when you do get a boneheaded error, right, your application's not necessarily crashing, I hope not, but you might be able to set safe states if you're controlling hardware and then shut your application down. It's a controlled shutdown based on an unexpected event. So Eric's next type of error is the vexing error or exception, which is an error thrown in a completely non-exceptional circumstance. Right? It's a wrench that's thrown into the execution of your code, and maybe all you can do is roll your eyes at it. Well, you can actually do more, right? What are these in LabVIEW? I mean, I think of a file dialog that throws an error 43 as a kind of a vexing error. It's like there's an output of that express VI that says the user canceled it. If I'm looking at that flag, it's also giving me an error. I now need to handle that error 43 or not wire it or filter it out. That might be a perfectly planned for and acceptable outcome in your application's execution. I'm not sure that that's really an error. And of course, the other example that jumped to mind is when you're reading from a serial port and you get this error or this warning that says there might be bytes remaining at the serial port. You might know for a fact that there are not bytes remaining at the serial port, but it's giving you that handy dandy error just in case. Now, last but not least, in fact, this was the type of error that led me on the hunt, that led me to Eric Lippert in the first place, the exogenous error. And I'll tell you why. At Composed Systems, we do a lot of, everything is solid. We are always striving for solid designs, from top to bottom in our software stack. We were having some very spirited discussions among the development team about whether or not it was cool to put side effects or functions that generate side effects inside things like constructors, class constructors. We have a convention for what that means among our development team. Or places like pre-launch init, when you're launching an actor in the actor framework. Exogenous side effects are side effects or errors that come from the outside world, right? We're talking to hardware. Most of us are using LabVIEW because we're communicating with instruments. We are manipulating things or reading things from the outside world, and all kinds of things can happen in the outside world that are completely beyond our control, like Godzilla, right? And these exogenous errors are otherwise known as side effects. Side effects is a very commonly used term in functional programming because we want to keep side effects out of our functions, to keep them pure, keep their execution predictable. It makes our software much easier to debug and much easier to reason about. Now, I just said, obviously we have to use software write software that communicates to real hardware, like robots and motors and all that stuff. So how the hell can I keep side effects out of my code? Well, this is not something we're going to get into in this presentation, but the answer is dependency injection. Not to be confused with the D in solid, which is dependency inversion. But the truth is, if you're doing dependency inversion correctly, you're probably going to get dependency injection for free. Dependency injection lets us inject at runtime the types we actually want to execute. This approach lets us write code where we can inject abstractions or partial abstractions into the software, exercise between things, unit test whatever we want to unit test, and not have to worry about robot driver errors or collisions with other things in the physical world. We can exercise the behaviors, the semantics of our applications without side effects, and then dependency inject real stuff in at the last possible minute to actually manipulate physical things in the real world. Okay. I'd like to talk about code smells. These are some code smells, that I'm looking for when we're doing team code reviews. These are the things I feel like I'm always busting people's chops about, and I'll wonder why I won't just shut the hell up about errors. But all right, what are code smells for these different types of errors? Well, fatal. If you're writing a bunch of code to handle an error like your Labview queue became invalid when there's no possible way it could be invalid, you're wasting your time. That's a code smell. Doing anything fancy with boneheaded errors, log it, capture it, make sure your application doesn't hurt someone by suddenly jerking a robot arm. But if you're doing much more than that, you're probably just guessing. Was there a question? Okay. With vexing errors, I think this one I'm going to cover a little bit better later in the presentation, but it fit here as well. Putting the remediation elsewhere, right? If I launch a file dialog, right, that is a synchronous call, it's blocking. I'm not going to get an error or a user canceled Boolean flag back until the user makes their choice. There's literally no good reason to handle that error anywhere other than right next to the function that generated that error, right? Error 43 means something else in the actor framework. So put it at the source. If you're going to launch that file dialog, it generates that vexing error. Handle the vexing error right where it occurs and move on. And don't let that error handling and the complexity of dealing with that pollute your code elsewhere. Because the farther you get from the source of that vexing error, the harder it is to understand why the heck it happened in the first place. And exogenous errors, the big smell for me there ultimately is, I think, an OpenClosed principle violation, which is you have some kind of error handler that's handling concrete errors from different sources, like 2 different kinds of database or 2 different kinds of motor controller. Like, if you are merging the functionality of handling those different errors from different concrete sources in one place, that's definitely a code smell. But I did mention event logs earlier, and I feel like these belong somewhere in the discussion about error handling, but maybe just as like a place to make a stylistic request or to think about the 2 directions of the execution of our code. Of course, we want to use event logs. And P.S., Paul Ross from Compose Systems has an amazing event logger that is dependency injectable, that supports dynamic sync injection, so you can start showing your events in different places and persisting them to disk at the same time you show them in a string indicator. Or he has network connectivity built into it, and it is just an absolutely beautiful tool to throw in your toolkit. So yeah, of course we want to use event logs. They are indispensable for certain types of reasoning about our code. We want them to be verbose, but not too verbose. And the most important thing they can give us when we're dealing with error handling and recovering from errors, unexpected errors in our event log, is for them to capture that first error as quickly as possible, to tell us it is an error, and then not blow up with 1,000 other downstream failures and confuse the hell out of us as we try to interpret the thing, right? So I think verbose logging is great, but blasting the log with errors, not so. And it's really the boneheaded errors that I think belong in our event log as errors. I guess asterisk. Paul's event logger uses other languages' convention of assigning criticality to the errors as they get logged, or the events as they get logged. So something can be informational, it can be for debug purposes, it can be logged as a warning, it can be logged as an error, where error is the most severe thing you could put in the event log. So empathy for myself, for future me, when I go back and I run that code 3 months later when the customer's hardware is finally ready. I've never once regretted putting the effort into that kind of information formatting. All right, we're stepping a little bit into another section of the presentation here. I want to talk about not all errors should happen in all places. Not all places should generate errors the same. Not all consumers of source code should have the same expectations about errors coming to them, right? So, a hardware driver is going to give us different kinds of errors than an actor from an API that we design ourselves and unit test. And a developer's integration test panel, has yet different expectations from all the other things. And I guess we'll just jump right in. All right, so a hardware driver. These things are highly concrete. They are prone to side effects, if not the main source or only source of side effects in our software. At this level of code, I'm not talking about hardware abstraction. I'm talking about hardware. I'm talking about an oriental motor motor drive that does specific work, that has specific bits and specific registers, and needs to be tickled in a particular way in order to reset the flags when a motor hits a soft position limit and generates a fault. Are so completely unique to the actual hardware that we're using. It is perfectly appropriate for this thing to do a lot of other things that other software modules would not do. Right. So just here's a code snip of the kind of error detail that I find very useful at this level of code. When this thing fails to do what I asked it to do, I spent a lot of time when I was making this code work, root out all the different things that could go wrong, where I send it a command and it refuses to move. So, if you're going to put in the effort, this is one of those things where I said earlier, and it sounds kind of corny, but you say every, there's all these idioms about failing fast and failing forward, right? Every failure in my code is an opportunity for me to go in and add some description. So when that failure happens the next time, assuming it's not a boneheaded error and it's exogenous, add some description about why that happened and what I can do to fix it. So when I ask this motor to move and it doesn't, I'm going to get a string that is formatted that tells me exactly why it didn't move. I am not smarter about this code after I wrote it. I'm totally dumb. And of course, our hardware drivers might also return mundane errors that smell like Visa errors or something, where I'm just calling some free NI Modbus over serial driver. But this is all okay. Like, we can't make everything beautiful and elegant and perfect. At some level, I'm talking to an instrument, and instruments return messy errors that might have a very wide range of codes. I'm not going to make everything perfect here. All right, so these hardware errors, they're unique, they're specific. It is my personal belief that the more detailed you can be, the better, especially when the information is there. It seems a pity to throw it away. And these are exogenous errors. What is the expectation of the caller? Well, it's just tell me what happened so I can try to fix it. I mean, we can't fix, if I try, in software, I try to move a motor and there's a Modbus error. I can't write every possible remediation to that. So that error might have to bubble up somewhere and get actually addressed by a human. That might be a showstopper. All right, so we use a lot of actor framework at Compose Systems. We have an open source separation of concerns framework that's built on the actor framework that smells most to me like model view model, but at the end of the day, it's still all actors, right? we write a lot of APIs that might use actors under the hood to perform some kind of asynchronous behavior, some kind of automatic error recovery. So actors can be concrete, they might be partially abstract. Before the era of proper interfaces in LabVIEW, we pretty much always had an interface class prefixed with a capital I that defined a message set, if you were an actor, so that all the descendants would have similar behaviors, similar semantics, similar interactions with the caller. And when you start writing code that way, you can have actors that do real work on abstract objects, and then inject concreteness when you're actually ready to do real work. So these may or may not be subject to side effects. There might be a lot that we can test and execute in an actor that has nothing to do with collisions in the real world. Well, one of the most important things that's different about an actor from just like a low-level hardware driver is that it's asynchronous. It has a lifespan of its own. When something wrong happens, an actor can fix it if it's something that we could have possibly predicted. And I'll talk a little bit about supervision strategy, but I don't want to get too much into that because it's a very deep topic on its own. All right, so as I just said, an actor can handle errors internally, right? I showed you, was, I guess, intentionally consistent with showing you a motor driver, right? This is an actor that calls that driver. This actor's behaviors are specific to the driver that it's consuming, because this oriental motor drive has its own unique remediations, right? There are certain things that can happen to that drive that need to be remediated in a very specific way. There are certain error codes that motor drive can return that mean something pretty specific. And by integration testing that, I have in this actual code several error cases. And I deduced through my testing that pretty much anything that comes back as a Visa error means the cable was unplugged. Like once you're connected to that thing, any error in these humongous ranges, the best thing that actor can do is just try to reconnect. And that is a recovery that actor can do without leaking details of its behavior or details of its error codes up to its caller. And so there's a huge role for handling errors internally within an actor when those errors are not part of an API that was agreed upon between the actor and its caller, and when those errors are exogenous errors that we could predict, or vexing errors that we could predict. You might have an actor that is a dialog box actor, and obviously it's going to have a possibility of throwing an error 43. So it doesn't have to be exogenous errors, but and I just point out what a diligent effort I made to format a string to explain to future me, who's a complete moron, what actually happened, so that I can help the customer solve the problem as quickly as possible. Right. The other scenario with actors is that they can provide a sort of API to their caller. This process step actor, this is the handle error method. Probably should have mentioned that for the previous screen as well. We're looking at the handle error overrides for these actors, the place where your actor handles whatever errors don't get filtered out before your method is done being invoked. I wrote this code a long time ago, but I thought it was a reasonable example. The agreement between process steps and the process model that launches them is that they are never going to return an error in their last ACK. They're always going to stop, and then elsewhere in the process model, we're going to take the last ACK value of that actor, sniff in there, and say, oh, well, did that step end with an error, or did it end successfully? It's just how I wrote it back in the day. But when you write code this way inside of an actor, you now have behaviors and semantics that are consistent between any descendant of this process step. assuming you don't override this behavior, but that would be a naughty thing to override and break this behavior. And you could certainly override and extend this behavior. There's not just one way, right? There are different scenarios, there are different reasons to treat errors differently, depending on what outcome you're trying to achieve. So ignoring supervision strategy for a moment, which I haven't even really talked about yet, actors should either, I think, actors should do one of these two things. That they should try to handle everything, do their best to recover. And maybe if they tried that and they couldn't fix it, they trap the error and either stop or become unusable. Right? So supervision strategy is an idea that my teammate Mache first introduced me to, and our experience with it comes mostly from Akka.net, which is an actor framework that implements a supervision strategy. The idea is, with this actor model of computation, that an actor might launch these delegate actors that do specific business underneath this owner. And that when you are building these micro hierarchies of functionality, there are different strategies for recovering from errors, like an all-for-one strategy, which is when one actor generates an error, they all get treated the same, they all get stopped, and they all get relaunched. Right? That's kind of out of the scope of this conversation, but I think it's really interesting and is yet another exception to the, well, that guy Ethan said that I think this is the right way to handle errors in actors. My point about supervision strategy being, we still need to think about open-closed principle when we write code that way. Right? Every time we put an actor, we launch an actor, we are giving ourselves the opportunity, an opportunity for abstraction. Right? You could launch a motion actor that uses a specific kind of hardware. The vendor could release a new kind of hardware that is similar, but ever so slightly different. And you could create a descendant to your original actor class. Right? As long as that descendant behaves the same way from the perspective of its caller, everything's cool. But if that descendant of this concrete motion actor returns different error codes up to its caller than the caller was expecting from the old type of motion actor, we have now broken open-closed principle, because we need to modify the caller to handle the new abstraction that we plugged in. Right? That is the classic textbook OCP violation, with the typical example that I provide being like a static factory pattern somewhere in the middle of the execution of your code. Oh, you added a new option. Now you need to go add a new case structure to instantiate a different object type. That's pretty dirty, and it's something that we can completely avoid by doing dependency injection correctly. All right. So when an actor returns an error to its caller, to me, it means one of two things. It means I'm dead, I died, or something really unexpected happens and I need you to fix it, which is probably going to end up in relaunching the actor or something pretty serious like that. All right, so stepping into yet another domain of thinking about errors. We write a lot of APIs. We write these session APIs that are by reference, data DVRs under the hood, where you might dependency inject some concrete stuff into that reference class, but that reference class gives you effectively a static API that you can call anywhere, and it lets you inject different concrete functionalities into that API. When you're going to spend that kind of time writing a programming interface, it is my opinion that you should spend just as much time thinking about the error codes as the error codes you're going to return, about the methods it should have, right? This is an example from the real world. We wrote this valve control client-server microservice architecture where I have a valve control client, right? I give it the recipe of how it's going to connect to a server. by giving it either concrete or abstract objects. And then I start up this by reference session. It looks like any other by reference session. I open it. I can make calls on the reference wire, and when I'm done, I close it. But when you're going to put that level of effort into designing an API, you can also use something like VI Tester to unit test and assert the error codes that can come back from it. So rather than showing you the API, I'm showing you here, well, I almost called it a unit test, but I'll slap myself later. This is really more of an integration test because I'm actually communicating between a client and a server using a 0MQ socket. But that's cool. It's kind of splitting hairs. Right? I'm constructing a server. I'm launching it, and when I'm all done, I stop it. And in the meantime, I instantiate this client type object with some other concrete object that is used to communicate to this real server. I open a session, and here's what this test is testing. This is a valve controller. We use design by contract implementation to make sure that the valve controller is always safe, that I can't activate valve A and B at the same time if that particular condition would cause hardware to crash into each other, So what I'm asserting here is that I can't deploy two safety contracts to my valve controller that have the same name. Right? That was something that I chose to bake into this as a designer. But here's my API. I open it, I close it, and I can assert and prove that when I do this particular thing that's wrong, I get this particular error. And as you saw briefly on the previous slide, I have a whole test suite of asserting the error codes that come out of my API when I do various stupid things to it. Because future me is dumb, and the person who didn't write this API doesn't know what the expectations are either. So this isn't just my idea, though. I think API errors should be general in nature. If you're going to write a clean API, I think they should be curated and not just any old thing, because that makes it really hard to intelligently handle the errors that come out of it. And they should obviously explain when helpful. But I'm using the Labview Q API here as an example. I mean, the documentation for this API tells us exactly what error codes can possibly come out of this function. And several of these are not possible with certain permutations of input. So I wanted to handle errors immediately downstream of this call. I know the superset of possibilities. Right, and I can get boneheaded errors out of this API, just as I can get boneheaded errors out of the API I showed you on the previous slide. And I can give it junk input, like a queue size of 0. That's an error. So I forget which of the codes this is, but and we just need to make sure that our code can still be readable when we make these errors. So when I deliver an API to someone else, I think one of these two interpretations should map. The error should map to one of these two interpretations. Either it's boneheaded, you can't do that, or oops, you're calling me. I'm an API. I tell you what the possible inputs are, and I tell you what the possible outputs are. So I'm going to give you a very concise error code that says, no, you can't do that. You can't have two of the same thing with the same name. Right? I'm not going to bubble up very low level, networking errors up to the client, because it's impossible to reason about my code if every possible thing that can go wrong in that entire software stack can bubble from the bottom to the top. All right. Last but not least, I'm sure you're all disappointed. I'm not actually going to talk about a developer's integration test panel, because we all know any error that we can get in that, we probably want to see, and we're going to do something real dumb and sloppy, like call a simple error handler, or just put an error cluster on the front panel. Right. The top level glue, the top level application is the glue that holds everything together. It does all the dependency injection. It does all of the important domain specific business. Of course, it can have side effects. However, as we've seen and experienced at Composed Systems, we can take dependency injection all the way to the top. We can dependency inject abstractions into our applications. We can inject similar abstractions into our microservice servers, and we can run all this stuff in real time, communicating, between servers and clients, and exercising the code. But when rubber meets the road, obviously, we're going to get real errors in our top-level application. So, what does that look like, right? I've been preaching about getting the right level of error detail and, making them verbose. And I got, a few months ago, I was writing code, this idea, which I'm going to talk about, this little GUID VI. We spent all this time documenting our errors, formatting them, making them really verbose and explicit, saying, hey, I can't connect to the such and such device at COM port 3. Why don't you check that the COM port enumeration is correct or that the cable is connected? Great. That's a super useful error. But here I have an API that's controlling valves. I have a top-level VI here that's getting executed inside of a process step. And inside that process step, I'm literally calling the same VI twice, right? As if I didn't hate call chain enough, right? I mean, I think it's the best thing available in general without doing work yourself. But when you get that call chain from a method that's called inside an active framework method that got invoked inside of a message do, you get an entire screen's worth of call chain that is so useless. It's just frustrating, right? You put that in an event log, and all of a sudden your event log's like flying across the screen faster than you can even see, because you've got this 3,000 character call chain. This is my answer to that, right? I could have done everything right. I can get a really readable error out of here. But the particular functionality at the top level, it means something. This is a concrete step, calling this API in a specific way, because on the customer's machine, after they install this gadget on the device, they want to extend the arm and then bring it back in to engage magnetically, I think, the widget that they just installed. If I get an error on the first call, that means a different thing than when I got an error on the second call. And oh, by the way, I'm also calling the same VI 1,000 other places in this code, right? So the top level is the world of concreteness. Everything's real there, and we need to embrace that fact. And when something never, I can run this 1,000 times, but when my customer runs this code and runs through this process, and for some weird reason, we get an error on this wire, and it's never happened before, they can call me and say, hey, I got this GUID 5970. I can do a control F in my source code and find the exact place that generated that error, if I didn't happen to put a string in that made it easy enough to read. So what is this function actually doing? It's just throwing a GUID tag into my error source string. And if I put anything in, an additional error description, because the context matters. These are not the same thing. They don't mean the same thing. They're not doing the same thing. So all this little VI is doing, and I put this 1,000 places in my top level code, is slapping a static GUID, which I paste into a string constant, and a tiny little description to augment the error code. So I have maybe a quick guess about where this actually occurred in my code, without having to rely on that heinous call chain string. I've used this approach with great success. I've even shown it to my colleagues, and they didn't laugh me out of town. All right, so I want to sort of wrap up here by talking about solid principles. I have a lot of opinions about things. I think a lot of those opinions are justified by the solid principles. If you don't agree, I'd love to hear why. If you are so bold as to tell me. All right. So let's talk about OCP, the open-closed principle. Classes should be open for extension but closed to modification. Well, the solid principles, you don't need to use object-oriented programming constructs to benefit from object-oriented design principles. Not following OCP makes your code suck in a major way, right? All you need to do to break open close is have an error handler like this. Right, this I'm just showing you the 3 different cases of this case structure. By default, we do nothing. We do this one special thing for MySQL, and for this other thing, we do something different for SQL8 because those errors aren't important. Well, presumably, if I have code like this, I'm dependency injecting, different database types, or using a hideous factory pattern to pick the static object that I want at runtime from the list of all the options, and I'm handling their errors differently. This is literally like the inverse. This is the mirror image of that ugly factory pattern that calls all the dependencies into memory, even though I'm only using one of them, right? This is all of the semantic garbage of all of those things dumped into one trash can. And if I want this to now handle, Microsoft SQL errors, because I added that as one of my options that I can either instantiate or inject at runtime, now I have to come to this section of code and modify it to handle yet another class of error, another type of error from a different type of concrete thing. Right? So this is the kind of crap that we want to keep down in our abstractions. We want to return errors that are generic enough that the set of possible concretions can agree on what they're returning, if we want reasonable error semantics in our callers.
Hey, Ethan, there was a question earlier about the grid. It was when you are writing the code, how do you create the grid constant?
So this hasn't been a thing long enough for me to properly solve that problem. It just so happens that the source code that I'm using in this project has a .NET GUID generator wrapped in a LabVIEW VI. So I just quick drop that, and I press run at the run arrow, and I copy and paste GUIDs in here. I was racking my brain for a way to automate this, right? When I throw this VI on a wire, ideally, I would be able to just throw it there and have a GUID pop up. So it's a little bit clumsy, I will be the first to admit. I have to generate a GUID with this little VI that's open and paste it into the string constant.
So right now
shame on me.
You do hope that you don't generate twice the same GUID, and luckily someone.
Yeah, right. As long as I remember to press the run arrow and copy a new GUID into that field, right? This is a guaranteed unique .NET GUID. I'm pretty sure the universe would implode if I got 2 of the same number by running that VI twice, or something like that. At least that's what I think would happen. But I don't think there's a way, right? I was racking my brain about using like object tags, like every unique instance of this VI that I placed could have like an embedded tag on its front panel that had a unique GUID in it, and I didn't really fully explore that idea. It was more than I wanted to get into at the time. For now, I'm perfectly willing to just paste a unique, obviously a unique GUID into that string control. And for me, the juice is worth the squeeze. It's not a big deal. But yeah, you have to wire that. And because I believe in super clean interfaces, if you don't wire at least a string constant to that input, it's going to break your code because it's a required input. The additional description is not.
Okay, and in terms of time, we have only 5 minutes left. I think the next team is going to come up soon, so maybe if you can wrap it up in the next 10 minutes.
Yes, I'm coming right to the end here. So LSP, I think the most reasonable way in the context of this discussion to say that is the way that it's worded at the top there. Right, this subtype should be substitutable. This is what I was talking about with actors before. And I really firmly believe that this principle applies at every level. Like, things should be fractal for things to make sense and be robust. So a VI shouldn't implement crap that it doesn't use. A class and an actor and an API. Sorry, I jumped to ISP. Liskov. Yes, let's talk about Liskov. right? So I have these two classes. I have cured meat and secret pepperoni, and they both implement this method, right? I might have an expectation of all my callers that anyone who calls this method to get the expiration date is just using error in and error out for data flow. Ugh, cringe. You shouldn't have inputs and outputs in your functions that are just for data flow. We don't need to do that anymore. That is very old-fashioned. And if secret pepperoni can return an error out here, and my code is never expecting an error to flow out of this expiration date call, that is a Liskov substitution violation at the VI or method level. Right? The semantic expectations of the left one and the right one are not the same for the two implementations. And last but not least, let's talk about ISP. Things should be lean, not fat, interfaces. But what is an interface, right? I just showed you the front panel of a VI. It has inputs and outputs. To me, that's an interface. You can mark things as must wire. You can mark things as recommended. But clients shouldn't be forced to implement things they don't use. Again, at every level. What is this crap here? If I don't use it, it shouldn't be here, right? So I'm giving this class permission to violate the contract that the base class has with all of its callers by giving it this input and this output, because it can put whatever it wants on this wire in between, and that's not cool. And I think this is my last slide with any actual content on it. If you don't know about synchronized data flow, this function over here on the left, the one that looks kind of like a terminal strip, you need to learn about it, because it is a malleable VI that lets you stop doing every single one of those dirty, kludgy, I'm using errors for data flow nonsense situations that we all did all the time. We don't have to do that anymore. We can just put any data type into one of these inputs and the same type comes out, and we can put an error or a reference or whatever we want into any one of the other inputs, and that same exact object comes out, and it lets us synchronize our data flow at this node. If you're not using merge errors more than you're using diagram around all your code case selectors to just not do anything all over the place, you probably should be using merge error more. If you don't know that you can format strings in error rings, congratulations, your mind is now blown. With this kind of string formatting, saying, hey, I couldn't connect to the device at COM port 7 is so much more useful than a generic visa error. And of course, the syntax of handling errors by number directly in case structures is just awesome. I mean, it's anything that simplifies the syntax of our code is great. And even though this is just a small improvement, it's a small improvement in 100 places in my project. And that to me is awesome. So thanks for sticking around. Thanks for paying attention. And thank you for your questions. I will jump into the breakout room if anyone hasn't had enough talk about error codes, which I think is highly unlikely, but I will be there in any case.
All right. Well, thank you, Ethan.